Power is a very important concept in the world of physics. We've heard the term power before, but in physics it has its own unique meaning, just like work does. In physics, power is the rate that work is done. We've seen that definition before, the rate at which something happens. Every time we see that word rate, the equation looks similar. On one side of the equation is the symbol for power, and on the other side, we always have time in the denominator. Since this is the rate at which work is done, we'll have work in the numerator. So power is work divided by time. Let's look at the units for that. Work, we know, can be measured in Newton meters or in joules. Time is in seconds. We actually have a new unit for power. The unit is a watt. 1 watt is equal to 1 joule per second. In problems where we're dealing with power, we will often have to find the work first and then divide it by time to find out how much power. Just as in our first example problem. A box, which weighs 575 newtons, is lifted a distance of 20 meters straight up by a cable that's attached to a motor. It takes 10 seconds to lift this box. What power is developed by the motor? To determine this, we're first going to find how much work the motor does. F delta x cosine theta. As we learned in class, when you are lifting something up, the force to lift is equal in magnitude to the force of gravity. So the work done by the motor is equal to that lifting force, which is equal to the force of gravity, 575 newtons, times the displacement of 20 meters, times the cosine of the angle between the lifting force and the displacement. This lifting force lifts my box straight up, and the box moves straight up. So the angle between them is 0 degrees. 575 times 20 meters gives me 11,500 joules of work. To find the power that this motor develops, I divide that work by time. 11,500 joules divided by 10 seconds gives me 1,150 watts. So this motor develops 1,150 watts. To determine reasonability of your answer here, think about other things that you know that are measured in watts. Light bulbs are measured in watts. They're commonly 60 watts, or 100 watts, or 40 watts. Your hair dryer may even have a watt rating, or a power rating on it. That can sometimes be as high as 1,800. So is this a reasonable number? Yes, this is a reasonable number. Moving on to the next problem. This time we're lifting an elevator. The elevator has a mass of 1,100 kilograms. We're lifting at 40 meters in 12.5 seconds. How much power does the elevator generate? This is just like the previous problem, but the only difference is now we're given a mass instead of a weight. Pause the video. Take a moment to see if you can figure out how to do this problem, and then restart the video after you're finished to see how you did. Again, for this problem, we have to find work first. Work is F delta x cosine theta. And again, the force in this problem is going to be equal to the force of gravity. We know the force of gravity can be calculated by m times g. So I'll plug that into my work equation. The mass is 1,100 kilograms. g is 9.8 meters per second squared. I'm using a positive number because there are no vector symbols. And we said when there are no vector symbols, we are not allowed to plug in negative numbers into our equation. So I multiply that by 40 meters, the displacement, and then times the cosine of 0 degrees because the force is up and the displacement is up. When I do that, I get the number 431,200 joules. If that were my final answer, that would have to be in scientific notation. But because it's not my final answer, it does not need to be. Power is work divided by time. So I take that number and divide it by 12.5 seconds. And I get 3.45 times 10 to the 4th watts. This one is in scientific notation because it's my final answer. Does that make sense? Sure it does. It's a pretty big number, but it's an elevator that we're lifting. And it's going pretty fast, 40 meters in 12.5 seconds. So that is a reasonable number. Moving on to the next problem. This one talks about accelerating a car uniformly from rest to 10 meters per second in 3 seconds. And we want to know how much work is done on the car in this time interval. A is a review of the work kinetic energy theorem, where the work, really the net work, is equal to the change in kinetic energy. Well, the change in kinetic energy is final kinetic energy minus initial kinetic energy. It tells me we're accelerating the car from rest. That means that the initial kinetic energy is 0. Kinetic energy is 1/2 mv squared, so final kinetic energy is 1/2 mv final squared. That's 1/2 times 1500 times 10 squared. That gives me work of 7.5 times 10 to the 4th joules. That's how much work it takes to accelerate this car. The power delivered is work divided by time. So 7.5 times 10 to the 4th joules divided by the time of 3 seconds. That gives me 2.5 times 10 to the 4th watts. Again, a reasonable number because I'm accelerating a very large object, and I'm getting it going pretty fast in a small period of time. Okay, so this is the end of power. In class, we will have the opportunity to do more examples using this power equation.